continuing with the course. Today we will discuss occupational probability and career concentration. In the last class, we have discussed about the density of states, rho of E, which was given by an expression 1 over 2 pi square into 2 mc by h cross square for valence band, for the conduction band, to the power 3 by 2 into E minus EC to the power half for E greater than EC. This was the density of states, and as I mentioned, the importance of density of states is to determine the carrier concentration, and we need to determine the carrier concentration to know the current, and carrier concentration is given by N of E dE, and where N of E is the density of carriers, and this is equal to density of carriers is equal to available density of states multiplied by the probability of occupation. The probability of occupation. So F of E here is the probability of occupation. We will discuss this probability of occupation in this class and determine the carrier concentration. The probability of occupation for electrons is given by statistical mechanics, is given by the Fermi function F of E is equal to 1 divided by e to the power E minus EF by KT plus 1. The probability of occupation of electrons in an energy level E. So electrons in the energy band, this is E, always the vertical axis is energy, this is EC, this is EV. Anywhere, if you take an energy level in the valence band, let us say E equal to E1, or if you take an energy level in the conduction band, let us say E is equal to E2, then if you want to find out the probability of occupation, both these bands have number of states, a large number of states. What is the probability of occupation of these allowed states? The probability of occupation for valence band as well as for the conduction band, probability of occupation by electrons is given by the Fermi function. So if you substitute, if you want to find out the probability of occupation here, E1, then you substitute E1 here. If you want to find out the probability of occupation E2 at the level E2, then you substitute E2 in this expression, where EF is a constant called the Fermi energy. EF is the constant called Fermi energy. So Fermi function, or it's also called Fermi-Dirac distribution, because it tells us, it indicates the distribution of electrons in the energy bands. So if you want to plot this F of E, as you know, in the valence band, the probability of occupation is very high. Valence band is completely full at 0K. At 0K, so this is EV and this is EC, and here is E. So this is the conduction band and this is the valence band. If you consider at 0K, I want to plot the probability here along this axis, F of E. Many times in solid state physics, F of E is plotted here and energy in this axis, but here for uniformity we will always keep the vertical axis E. So if you plot F of E here at 0K, how would it be? that the valence band is completely full, which means the probability of occupation of every state is 1 and the probability of occupation here is 0. And as you know that if EF remains somewhere here, it can be anywhere, but if EF is here, then the probability of occupation is 0 up to EF, and for E greater than EF, the probability of occupation is 1. So in this axis, this is 0, f of E equal to 1. So what I have plotted is the f of E as a function of f of E as a function of E. For E greater than EF, probability is 0 and E less than. There may not be a level. If there were a level at EF or anywhere here, for example, probability equal to 1 here, what does it mean? There is no level. There is no state permitted. If there were to be a state, then the probability would have been 1. But all the levels here are completely full, completely occupied. Probability is 1. If you take a finite temperature, this is what you already know, that if you take for any temperature at E is equal to EF, that is at this level, at E is equal to EF, for any temperature, the numerator is 0 and therefore e to the power of 0 is 1, 1 plus 1, or the probability is half. So f of E equal to half for all T. For all temperatures, f of E equal to half. So if I indicate that half here, so this is 0.5. Please see, I am plotting probability on this axis, f of E. If this is half, then if you take any finite temperature, we know that the electrons from the valence band make an upward transition here. There is a finite probability of finding electrons in the conduction band, and probability function is still described by the probability distribution is still described by the Fermi function, and the Fermi function gets smeared. This step function now gets smeared, but passes through the same point. So this is f of E. You can actually plot this numerically, you can plot this, numerically calculate and plot this for any temperature. So this is for a finite temperature T, T greater than 0. What it indicates is there is a finite probability here of occupation of these states in the conduction band. This function is f of E. What is 1 minus f of E? If f of E is the probability that a state is occupied, then 1 minus f of E is the probability that the state is vacant, unoccupied. The state is vacant. In the valence band, if 1 minus f of E, please see, it is f of E is going like this. Therefore, if I take an energy value E1 here, let me draw afresh. F of E is the probability of occupation. Therefore, 1 minus f of E is the probability that the state is vacant. So, if I plot again the same graph, but I am plotting again. This is EV and this is EC. The Fermi function at a finite temperature is varying like this. So this is the line f of E, this is f of E. Now on the x-axis I have f of E, vertical axis is E, energy, and 0.5 is somewhere here. Therefore EF is somewhere here, EF. At any given energy value E1, I find out what is f of E. This is the value f of E here. say for example 0.9, 0.9. Say f of E is 0.9, which means the occupation probability of the energy level E1 is 0.9, which means the probability that the state at E1 is vacant is 0.1, 1 minus 0.9 is 0.1. That is this one. See, this magnitude here, if this magnitude of this length is 0.9, then this is 0.1. This is the probability that the state is vacant. A vacant state in the valence band represents what? It's a hole. Therefore, 1 minus f of E represents the probability of occupation of a hole. 1 minus f of E is the probability that the state is vacant, which means as far as valence band, we don't talk of a hole in the conduction band. For example, let me take here at some value E2. E2 is a value in the conduction band, energy value in the conduction band, some value E2. This may be some number, let us say 0.05, for example. So probability of occupation here is 0.05. What is the probability that there is no occupation? The probability that there is no occupation, that is this one, 1 minus f of E is 0.95, because this is 0.05. Therefore, this is 0.95. That is not the probability of occupation of a hole, but that is the probability that the state is vacant. So please remember, f of E is the probability of occupation of electrons, whether in the conduction band or the valence band. But 1 minus f of E is the probability of occupation of a hole if you are talking of the valence band. Otherwise, it is the probability that the state is unoccupied. So 1 minus f of E is the probability of occupation of a hole. Of a hole in the valence band, obviously. At a finite temperature, there is always a probability that there are some electrons in the conduction band and there are some holes in the valence band. Of course, depends on the band gap, Eg. If Eg is very large, let us say 5 electron volts, then the probability of finding an electron here may be 10 to the power of minus 20, which means literally none. But for normal semiconductors, Eg is of the order of 1 electron volt, which means there is a probability of finding electrons here. So the second thing that you have to see is, this is Ef, then the curve looks something like this. Please see, let me indicate first graphically, because graphically it becomes very clear. This axis is f of E and this is 1 probability and this is 0, and at E is equal to Ef, this is 0.5. If Ef is towards EC, this is EV. If Es shifts towards EC, that means the probability function, because this point at E is equal to Ef. So let me draw a second value of Ef. This is Ef0. Let me call this as Ef1. For another material, if Fermi function is Ef1, it means this point of probability of half should come here. That means this should shift further up. So I will have, the curve will remain parallel. Please see that the curve remains parallel, this one, but it is shifted up. What does that mean? And clearly the curve shows that now the probability of occupation of electrons in the conduction band is more, and probability here has become very small. 1 minus f of E, number of holes here will be very small, probability of occupation. On the other hand, if the Fermi function were to be here, let's say E is equal to EF2, that means this curve would shift down, because there is nothing else in the Fermi function other than EF. It is simply e to the power E minus EF by KT plus 1 divided by. So that this means that the curve is now shifted downwards. So you have the 0.5 coming here, and you see now the area under here is quite large. It means there are larger number of holes in the valence band. So graphically it is very clear. Of course, in mathematics, if you put, it will show you the numbers. One thing which I would like you to do is, if you shift this EF here, I have shown it like this. It appears as if the probability is very large, because please see, this is 1, because it is 0 to 1 here, 1. This appears as if this is 0.2 or maybe this is 0.4. But just put numbers in this Fermi function. For practical p-type material, practical n-type material, and you see what is the kind of numbers that you get. E minus EF by KT plus 1. Choose some suitable temperature, say 300 K, and put numbers and try to plot this. You will be surprised that here I have shown it is as if 0.4. This will be very, very small number. The probability here is extremely small. This will come out 10 to the power of minus 4, minus 6. That kind of number, literally you cannot see anything like this. It will be actually, in an actual graph, it will be as if it's almost 0 everywhere, almost 0, and then it goes like this, and almost 0 everywhere, because the probability of occupation here is extremely small at normal temperatures. But we have large number of electrons. How is it possible? At room temperature, if you take silicon, then the number of electrons, the carrier concentration there is of the order of, for silicon, it is of the order of 10 to the power of 10 per cc. Concentration, Ni, intrinsic carrier concentration at room temperature is of this order. But I am saying that the probability is very, very small. How is it possible? Because N is equal to rho of E into F of E. The density of states is very large. In the last class, I had calculated N, the total number of states, from EC to EC plus 0.1 EV. Has anybody tried to complete that integral? So EC to EC plus 0.1 EV. This I called as N, and I had asked you to calculate what is the number of states. The number of states was of the order of 10 to the power of 18. I think 2.5 into 10 to the power of 18 is the numbers. Please do numericals. It's very important, because there will be numericals in the exam, and more importantly, you are handling 10 to the power of minus 34, 10 to the power of minus 19, 10 to the power of minus 23. So unless you practice, you will not be able to do the numerical correctly. Every one of you will get a different answer. So please practice numericals, because there are huge powers you have to handle. So the number of states itself is very large, and therefore even though the probability here is very small, probability actual number is very small, multiplied by the number of states, it is significant. It is still of the order of 10 to the power of 10. So this is the distribution or occupation probability. Of course, we are aware of this, but I am just recalling all the concepts that is essential. Therefore, the carrier concentration N is equal to rho of E into f of E dE. Let me consider N is the carrier concentration in the conduction band. So this is EC to infinity. I am writing EC to infinity. Actually EC to certain value, some value of the band, but I am writing it up to infinity because, as I mentioned to you, the numbers here are extremely small. Larger the difference EC minus E here, smaller will be the probability. That is, this term goes to 0. It does not matter. You write EC, this may be up to EC plus 2 EV or 1 EV. But f of E already goes to 0. Therefore, it does not matter whether you integrate from EC to EC plus 1 EV or EC to infinity. It is one and the same. That is why I am writing the total number of carriers in the conduction band as N is equal to EC to infinity. So substitute here rho of E integral 1 over 2 pi square 2 mc by h cross square to the power 3 by 2 into E minus EC to the power half into f of E. So 1 divided by e to the power E minus EF by kT plus 1 dE. EC to infinity. This gives us the carrier concentration. Before I carry out the actual integration here, this is actually not possible to integrate analytically. All right, let me continue with this. So let me take out 1 over 2 pi square into 2 mc by h cross square to the power 3 by 2. Constants I have taken out into integral EC to infinity E minus EC to the power half 1 divided by plus 1. This can be integrated only numerically, but we can make some simplification. You add and subtract EC here in the denominator, and this divide by kT. So this is equal to 1 over 2 pi square twice mc by h cross square to the power 3 by 2. So I add and subtract EC, and then we put E minus EC by kT equal to eta, and EC minus EF by kT equal to eta F in the lower. So this gives dE is equal to d eta into kT, and substitute in the expression. Further, when E is equal to EC, this is 0, please see, E is equal to EC, then the lower limit is 0, and when E is equal to infinity, it still remains infinity. So I have 0 to infinity eta to the power half into d eta divided by e to the power eta minus eta f by kT, eta minus eta f plus 1. So eta is already dimensionless plus. These are the substitutions. You make these substitutions and you see that you get this expression. And outside you will have 1 kT coming from here and 1 root kT coming from this. So you will have kT to the power 3 by 2. Please do this substitution and see. So you will have this equal to 1 over 2 pi square into twice mc by h cross square into kT to the power 3 by 2 into this integral here is called the Fermi-half integral, f half of eta f. F half of eta f. This is called, this last term is called the Fermi-half integral. I will come to the simpler Boltzmann approximation, but because I had written the complete expression, I thought I will give you the rigorously correct solution. So this is n. There is no approximation in this. So Fermi-half integral. This has to be evaluated numerically. You cannot, there is no analytical solution. This has to be evaluated numerically. So we have 1 over 2 pi square, 2 mc by h cross to the power 3 by 2, kT to the power 3 by 2. Please see 1 kT coming from here, square root of kT, and 1 kT coming from here. So that's why kT to the power 3 by 2. Okay? Eta and eta f are dimensionless. That's why it is e to the power of eta minus eta f. This is energy dimension, this is energy dimension, so eta is dimensionless. So this is called the Fermi-half integral. So if you have to actually calculate the carrier concentration for any value of EF, whether it is highly doped or lowly doped does not matter, this is the rigorously correct solution. Fermi-half integrals. There are approximations which are available. The Fermi-half integral varies. I'll just show you what kind of values are we talking of for the Fermi-half integral. Just to get an idea whether we are talking of hundreds or thousands, millions, what kind of number is this? So this Fermi-half integral varies approximately. I'm just showing you approximately. So this is Fermi-half integral of eta f versus eta f. Because it's already integrated over energy, therefore it simply depends on the position of eta f. Where is the eta? And eta f is EC minus EF by KT, which means it simply depends on the position EF. So at eta f is equal to 0, so this is eta f is equal to 0. These are approximate numbers, but just to get you an idea, so this is approximately 0.1. Give you some idea that what kind of numbers are we talking of. So this is 0, this is 10, so 0.1, 10 power minus 1, 10 power minus 2, 10 power minus 3. The numbers are 0, here this is 0 around eta f equal to 0, 2, 4, this is minus 2, minus 4, and so on. Typical numbers for the Fermi. Eta f is equal to 0 means what? EF is at EC. The Fermi level has entered the conduction band. At EF equal to EC, eta f is 0. The Fermi integral is approximately 0.1. Approximate numbers, please. This is just to give you an idea what kind of numbers are we talking here. So let us say the Fermi function has just entered the conduction band. So this is your EC and EV in a highly doped, semiconductor. So EF has also come here. Then eta F is equal to 0, and this is approximately 0.1. So you substitute 0.1 and put all the other numbers here, and you get the carrier concentration. So this is the exact way of calculating. But we are also familiar with the Boltzmann approximation, which is quite simpler. I come to the Boltzmann approximation. So what is the Boltzmann approximation? Boltzmann approximation. Any doubts? Which one?
0.1081.
This one?
0 should be 1. 10 power 0.
Yes. So let me write in terms of 10 power 0, 10 power 1. Yes. That's right. Yes, that's right. Because if it becomes 0, then carrier concentration will become 0. It is 10 power 0. So please make a correction there. If Fermi integral is 0, then carrier concentration is 0. And at this value, such a high value of eta F, if that becomes 0, then yes. So the Boltzmann approximation, please correct that. Normal doped semiconductors, if you take an n-type doped semiconductor, then EF may be somewhere here. You take gallium arsenide or silicon, so this is EG is approximately of the order of 1.42 for gallium arsenide, and it has already moved towards the conduction band. Let us say this difference here is about 0.2 EV. I put some numbers because numbers make it more clear, that is why I use numbers. So 0.2 EV. Let us say the difference here is, it has already moved closer to conduction band because it's a n-type material. So N gallium arsenide. The probability of occupation F of E is given by 1 divided by E minus EF by KT plus 1 in the conduction band. So in the conduction band, E is greater than EC. E is greater than EC for conduction band. This is valid for both conduction band and valence band, but for conduction band, E is greater than EC. So if you substitute E here, then E minus EF is always greater than, for this particular example that I have taken, E minus EF is greater than 0.2 EV. At room temperature, so E minus EF is greater than 0.2 EV. I am writing this for this particular example that I have taken. E minus EF is greater than 0.2 EV. And KT at room temperature is nearly equal to 0.026 electron volts. 0.026 electron volts. Which means this exponent here is 0.2 divided by 0.026, which is approximately 8 is the exponent. So you have e to the power 8 plus 1. e to the power 8 is a very large number compared to 1. E to the power 8 is much larger compared to 1, and you can neglect this 1 compared to e power 8. And therefore, this I can write approximately equal to, for E minus EF much greater than KT, I can neglect 1 in comparison with this, and I can write this is equal to E minus EF by KT. This is the Boltzmann approximation. In Boltzmann approximation, the Boltzmann approximation is valid when E minus EF is much greater than KT. When E minus EF is much greater than KT, then 1 is neglected in comparison to this number, and therefore we write this as approximately equal to E minus EF by KT. If you substitute this, then that integral is easily integrable. This is true for both conduction band and valence band. The only requirement is E minus EF should be much greater. For EF minus E, for the valence band, EF minus E should be much greater than KT. Then N is equal to all those constants, 1 over 2 pi square, 2 mc by h cross square to the power 3 by 2 into integral EC to infinity. We had rho of E, which is E minus EC to the power half, into e to the power E minus EF minus E minus EF here by KT dt. Let me erase this. It's not required. Let me rub this off. This is now integrable. It's easily integrable. So E minus EF by KT. So how do we integrate this? Follow the same procedure, add and subtract EC. Some of you would have done this already. So please, so E minus, this will become E minus EC by KT into E minus EF minus EC by KT, added and subtracted for this term, and then we can put this as x. Then I will have this equal to 1 over 2 pi square 2 mc by h cross square. Let me complete the algebra here, and integral 0 to infinity as before. I am putting this equal to x. Therefore, at E is equal to EC, lower limit, it is 0. So, 0 to infinity. This will be x to the power half and e to the power minus x dx into this term outside. Okay, let me keep it here. E to the power EF minus EC by KT. Any other term? Any other term? KT to the power so dE will contain 1 KT to the power half. So KT to the power half, right? So KT to the power half. So simplify this. You should be getting an expression like this: mc KT by 2 pi h cross square to the power 3 by 2 into e to the power EF minus EC by KT. please simplify this and check that n is equal to 2 into mc kt by 2 pi h cross square to the power 3 by 2 into e to the power f by kt. So this is under the Boltzmann approximation. Exactly like this, if you follow for the valence band, you get expression for P is equal to 2 into mv kt by 2 pi h cross square to the power 3 by 2 into e to the power ef e to the power ev minus ef by kt. This is sometimes denoted as Nc for the conduction band, and this is denoted as Nv. Please see that it contains everything is constant except the effective mass. Effective mass Mc in the case of Nc and effective mass Nv in the case of Mv in the case of Nv. If Mc equal to Mv, both constants are the same. This is a very large number. If you put numbers, you will see that this will be 10 to the power of 18, 10 to the power of 19, or very large number, this part. Sometimes you get into a doubt whether it is EF minus, maybe you have made a mistake, and EF minus EC or EC minus EF. How do you verify? EF minus EC, so this is for the conduction band under Boltzmann approximation, which means my EF is somewhere here. This is EC, this is EF under Boltzmann approximation. So EF minus EC is negative. EF is smaller, EC is larger, so this is negative. Therefore, this quantity will be e to the power negative, which means a factor less than 1. And the factor has to be less than 1 because the carrier concentration that I am talking are of the order of 10 to the power of 10, 10 to the power of 12. And if this number is very large, 10 to the power of 19, naturally this number should be smaller, much smaller than 1. And therefore, it is correct that it is EF minus EC. A cross check, a quick cross check. Sometimes by using a negative sign or something, you would have got this as EC minus EF. If this becomes EC minus EF, this is a positive number, much greater than KT. So this will also give e to the power of 8, e to the power of 10, which is a very large number. So this is correct. All right. I will stop here because we have to take a quiz today, right? A very simple quiz. So please take a sheet. This is a very simple one. And please write your name first, lest you forget. Define rho of K, the density of states. And B, what is the unit of rho of K? Define precisely rho of K. In the last week, I think we would have defined at least 10 times, so I'm sure it will be there with you. Those who have finished, you just give it to me and you can leave.